Assalamu alaikum. Welcome back. We're continuing with our fine-tuning of the universe lecture series. We're now on lecture 7, and we are going to begin a new set of topics now. And this lecture is titled Introducing the Standard Model, Part 1. Before we get to talking about the material for this new portion of the lecture series, let us just do a very important recap of where we left off. The last thing we talked about when we were talking about the precision of the initial conditions of the Big Bang was the amazing number that Roger Penrose, Nobel laureate in physics, had calculated regarding the extremely low entropy that the Big Bang must have had for our universe to be capable of supporting life and to be what it is. And basically, we were talking about two different definitions of entropy that are both closely related. One is the ability to do useful work. So we talked about how our sun gives us low entropy photons. We use those photons to lock away chemical energy, for example, in plants. And it is that chemical energy that then gets broken down to provide the energy of all life. So energy for all life on Earth comes from the sun. The energy of the sun comes from the low entropy of the Big Bang. We touched on a second aspect that we should just flesh out here so that we kind of understand how astounding it is. We said that another definition of entropy is that disorder always increases. So that if you watch a video of an egg falling and breaking on the floor, you know what came first. The egg's on the table, then it rolls off, then it falls and splatters on the floor. If that movie is run backwards, you know that something is wrong. However, if we take a look at a bunch of molecules crashing into each other and bouncing off and film that for some time and then run that movie backwards, we would never notice that anything is wrong. Why is that? Well, because as physicists say, the equations of physics are all time symmetric. Time can run forward in the differential equations that make predictions, but if you put in negative t, you can also run time backwards. So the laws of physics seem to be symmetrical in time, but the universe is asymmetrical in time. Time runs only forward. So why is it that the laws of physics, which seem to govern the universe, can run forward or backward in time, but the universe can run only forward in time? Well, we said that that is because of the statistical law of increasing entropy, or the second law of thermodynamics. And to have this situation of time symmetric equations that can run forward or backward, but they only run forward, means that the universe was set at such a low entropy that whenever that entropy changes, statistically, it has to increase. And so that argument, of course, is much more involved than this simplified description. But the bottom line is, both for the universe to allow useful energy that can sustain life, and for the universe to have time run only in the forward direction, the entropy was so low that the Big Bang had to be so special that Roger Penrose calculates the specialness of the Big Bang was at least 1 part in 10 to the 10 to the 123. And so the Big Bang was not a haphazard explosion. And as far as I know, this number, how special the Big Bang had to be, is the largest number ever calculated in a physics situation. So I just wanted to kind of recap that before we move on and to highlight that, yes, when we're talking about fine tuning, we are not talking about very specific verses in the Quran, but we are trying to get a sense of how miraculous verses like these are. From Surah Al-Rahman, أعوذ بالله من الشيطان الرجيم, وَالسَّمَاءَ رَفَعَهَا وَوَضَعَ الْمِيزَانَ. And the firmament he has raised high, and he has set up the balance. The translation here is of justice, and as we talked about, that is, of course, one meaning, perhaps the main meaning, but another way to think about it is the very delicate balance of the physical structure that has allowed this universe to exist. And perhaps more directly to that point from Surah Al-Qamar, إِنَّ كُلَّ شَيْءٍ خَلَقْنَاهُ بِقَدَرٍ. Verily, all things we have created in proportion and measure. And when we talk about fine-tuning, we begin to understand just how precise this proportion and measure is. So where are we going next? Well, now that we have talked about initial conditions of the Big Bang, we now want to begin talking about the constants of nature and understand how special they had to be. And they include things like the masses of the fundamental particles and the strengths of the fundamental forces that govern how those particles interact. And so to begin that, we need to all kind of be on the same page about what are those fundamental particles and what are those fundamental forces. And that has been an ongoing description. It is by no means complete, but it has been a phenomenal intellectual journey of the 20th century for physicists to develop what is sort of prosaically named the Standard Model of particle physics. The name probably doesn't do justice to how brilliant and involved this model is, but we need to get just a passing acquaintance with it for the things we're going to be talking about. And so to do that, let us begin at a beginning that I think we are probably all familiar with, and that is that all things, all material things are made of atoms. And we now take that for granted, but at the beginning of the 20th century, this was not taken for granted, and many first-rate physicists did not believe in the existence of atoms. It is, of course, a very fascinating story about how atoms were discovered and their existence proved. And finally, with electron microscopy, some of them visualized. But in any case, that is a detour that we will not be taking. But I think we all remember from school now that matter which seems continuous, like the desk that I am now knocking on, seems like it's solid wood, is divisible into molecules, and they are further divisible into atoms. And a cup of water or a bottle of water here that we may be drinking, the water seems like you could keep taking smaller and smaller and smaller portions of it ad infinitum, but we know that eventually we will get down to one single water molecule, and there's no smaller unit of water, and that single water molecule is made of 2 hydrogen atoms and 1 oxygen atom. So we all remember that matter is made of atoms, and that atoms further, after their structure was elucidated, were discovered to be made up of a central nucleus, and that nucleus is made up of protons and neutrons, and orbiting that nucleus are electrons. And of course, you will read a lot of descriptions about how amazing this structure is and how much of the atom is empty space. So that, for example, the way to visualize it may be that the nucleus would be the size of a basketball inside all of LAX. So if LAX, Los Angeles International Airport, were basically around its perimeter, the atoms were flying around, the nucleus at its center would be the size of a basketball. So atoms are essentially so much empty space with a very, very small nucleus surrounded by a shell of atoms orbiting at relatively very far away distances. And that nucleus is made up of protons and neutrons. And so this is what we remember from our, I think, high school education, grade school education, what have you. And to flesh it out just a little bit, we also remember that this nucleus made up of protons and neutrons, that the protons are positively charged and the neutrons do not carry a charge. They're neutral and they're packed in together, and spinning around the outside are the electrons, which are negatively charged. And it is the electrical attraction between the positively charged protons and the electrons, which are negatively charged, that give us this sort of planetary model of the atom, if you will, like the sun attracting the planets. But instead of the force of gravity, it is the electromagnetic force between the positively charged protons and the negatively charged electrons. So that, I think, is, we're all on the same page with that. And now let us remind ourselves that these atoms come in 92 naturally occurring varieties. So there are 92 naturally occurring atoms, the last one being here, uranium. And these 92 naturally occurring elements, each atom, each kind of atom is its own element. So hydrogen is an element, helium is an element, lithium is an element, beryllium is an element. Of course, we're familiar with carbon, nitrogen, oxygen, and so forth. From these 92 naturally occurring elements, the PubChem database says that there are somewhere over 60 million compounds, and they come from different combinations of these 92 naturally occurring elements. And these compounds make up everything that we know. So all of the building blocks are 92. Well, you may wonder, why are there more elements in the periodic table than the naturally occurring elements? Like, for example, americium, what is that? Well, these are sort of man-made or synthetic elements done by high energy collisions that build up higher elements, but these are all quite unstable and will decay into the naturally occurring elements. And of course, some of the naturally occurring elements themselves undergo radioactive decay, like uranium. So let us then remind ourselves, what makes one element different from another? Why is carbon different than oxygen? Well, we've already talked about the structure of each atom. Each atom is a bunch of protons and neutrons in the nucleus with outer electrons spinning around in different electron shells. And what makes one element different from another is the number of protons. So carbon, which is diagrammed here, has 6 protons. The most common form of carbon also has 6 neutrons. So it has a total of 12 nucleons, 12 particles in its nucleus, 6 protons and 6 neutrons, but its identity is determined by the 6 protons. There are other so-called isotopes of carbon and of many of the elements that have the same number of protons, because for it to be carbon, it has to have 6 protons. That's not negotiable. But the number of neutrons is negotiable and variable. So our common form of carbon, the vast majority of carbon in our bodies, is carbon-12, 6 protons and 6 neutrons. But there are other forms of carbon, like carbon-14, which has 6 protons and 8 neutrons, and that carbon is radioactive, and it is the basis of carbon dating. So when an artifact is unearthed, for example, in, say, an Egyptology dig, and people want to find out how old it is, they look at the decay of carbon-14. Again, another sideline that's very fascinating that we won't be taking, but carbon, this number 6 here refers to the 6 protons. Oxygen, you see, has a number 8. So oxygen has 8 protons, and that's what makes it oxygen. So each of the different elements is distinguished from the other elements by the number of protons, and it is the number of protons that determines the identity of the elements. And the number of protons determine the number of electrons. When there are 6 protons, there will be 6 electrons because naturally occurring compounds are electrically neutral. So these electrons are arranged in so-called shells, and it is the interaction of the electron shell, the outer electron shell of one element with another, that allows chemical bonds and allows complex chemistry and allows all of life as we know it. So we will have a nucleus with electrons. The outer electron shell, for example, of carbon, will interact with the outer electron shell of oxygen, and 2 oxygen atoms can come in and share their outer shell electrons with carbon and make CO2, carbon dioxide. The outer electron of hydrogen, it is the most basic element with only 1 proton and therefore 1 electron, and the common form of hydrogen has no neutrons. 2 hydrogens can come in and share their outer shell electrons with the outer shell of, hydrogen doesn't really have outer shell. It has 1 shell with 1 electron, but it can share that electron with the outer shell of oxygen and make H2O. And so that is how chemistry occurs. And when we have chemical reactions, the elements sort of reshuffle and recombine in different ways. So for example, glucose, C6H12O6, can combine with oxygen and give us CO2 and water. And when that happens, energy is released, and that is the sort of energy that we live on. So all complex chemistry, all life, is based on this atomic structure. And for now, we will say that everything is made up of 92 naturally occurring elements, but we can simplify that each of those is made up of neutrons, protons, and electrons. So in reality, we could think of everything in the universe as being made up of 3 elements: an electron, a proton, and a neutron. And for the longest time, this was thought to be the end of the story, until the Standard Model was ushered in, and we realized that first people thought the atom could not be divided. Then they realized it actually could be divided and broken down into more basic constituents, electrons, protons, and neutrons. And they thought that these were now the most basic fundamental building blocks. But as science progressed, as the amazing ingenuity of humanity progressed, we discovered that actually there is something even more profound, even more subtle underlying this very basic structure. And in the next lecture, then, inshallah, we will take that up and talk about the Standard Model and what we currently believe at the current threshold of knowledge to be the most basic structure of the universe. I hope to see you then, inshallah. Take care and salamu alaikum.